Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. Hello.
Hello. Wait, there we are.
There we are.
I didn't have it, but now I had it. I'm very good at this, as you can see. I'm a professional video streaming person.
I thought I made it. I thought we decided we got this new thing because it could just be a one click and then we automatically transition.
I really thought that was what was going to happen, and it's like I turned the video on, and then it was still the beautiful floral background, and I don't know what's going on. I'm really bad at this, as you can all tell.
It's all good. It's all good.
Yes. Well, welcome everybody.
Yeah, welcome to another episode of Ask Us Anything about electrochemistry. We have some questions from last time as well as questions from earlier this week, and although we did get to answer all the questions from Neil's webinar from yesterday, no, not yesterday, 2 days ago, yeah. Wednesday. And some of those videos are still on YouTube. So if you want to watch them and catch up on some EIS circuit fitting, you can do that on our YouTube channel. We are streaming from LinkedIn and X as well as YouTube. Type your questions in and we'll answer them as soon as we possibly can. We do have a question already from Neve. And Neve is asking, please explain the working of glucose sensor used in CGM, like how it works with working electrode as platinum, reference electrode as silver, and counter electrode as like a platinum carbon. I don't know what CGM stands for.
I don't know what that is either. So that was something probably I don't know if we need some clarification or something. I don't know what CGM is either. Yeah. So anyway. I mean,
but we can still describe how a glucose sensor works fundamentally, with say a working electrode as platinum and a reference as silver chloride, and the counter electrode as being platinum or carbon or something like that. We can certainly do that. Do you want me to handle this?
Yeah, I was gonna say if you want to.
Sure.
I think there was one next one I was gonna do. But anyway.
Yeah. So the way that a glucose sensor works, and actually let me see, because we have a lab on this, on a glucose sensor. So let me pull that up quickly, and by quickly I mean taking lots of time to search and find it. So
not quickly.
So not
in any sense of the
term.
Not
quickly in any sense of the term.
No,
okay, so hopefully people can see this.
Yes.
This is a lab that's written. It's a PDF, but if you just type Pine Research and then type glucose, this should be one of the first search results. It's a lab that we developed a long time ago on basically electrochemical enzymatic determination of glucose in beverages. And the mechanism by which this happens, the electrochemical detection, is outlined in this article. But in general, the way it works is this reaction here. So you use an enzyme, glucose oxidase, which is either on, you can add it to a solution. Some people add it to, say, an electrode in some cases. But when you have glucose in, say, a beverage or some kind of drink, and I'll zoom in a little bit more, there are these two forms of glucose that I believe are in equilibrium with one another. They may or may not be. Or actually, there's just a combination when you have glucose. When you buy glucose, they come in these forms, just as the sugar. A reaction occurs between glucose oxidase and this beta D glucose. Now, I should mention right from the start, I am not a biochemist, so I do not understand or know the biochemistry in any great detail. I'm an electrochemist by formal training and more of a P chemist, if it's anything. So this reaction, all I'm going to say is that you use an enzyme with beta D glucose, and what that does is it takes water, oxygen, the glucose, and then it forms peroxide and then glucon gluconlactone gluconlact this
That
guy
thing.
that guy. And so you have this reaction, and in short, the amount of glucose that you usually have enough glucose oxidase as an enzyme in your system so that the amount of glucose you add is the limiting factor. You have an excess of glucose oxidase, and you run this reaction very quickly. This reaction to form water, oxygen, and peroxide happens very quickly. And it's this peroxide here that actually allows you to, this is what we measure electrochemically. So we determine how much glucose we have based on how much peroxide we generate. And I don't know if the reaction is here. This is a little bit of background on fructose, glucose, and sucrose. This is kinetics of actually the enzyme. Okay, so it doesn't actually have, here we go. This reaction here. So this reaction here is peroxide plus oxygen. There's an oxidation reaction of peroxide to form oxygen and 2 protons and then 2 electrons. This oxidation reaction happens on a platinum electrode. So because this is an electrochemical reaction, we can measure the current. And in this particular lab, we use chronoamperometry to actually measure the concentration. This C naught or C star O is the concentration of glucose, and based on the current that you get, the area of your electrode, the diffusion coefficient, and just how much time has passed, will tell you what it is. And so most glucose sensors operate by creating a concentration profile, or more of a calibration curve, where they measure known quantities of glucose with glucose oxidase and measuring peroxide. They create a calibration curve with known concentrations, and then they measure the current at a specific time that they've designated. And then, assuming that you have a linear relationship, and in this case, you should have a linear relationship between them, you create a calibration curve, and then when an unknown amount of glucose is consumed, you can then correlate the current to a known concentration. So fundamentally, that is the basic idea of how a glucose sensor works. And so a lot of researchers will either use platinum. I don't know if glucose sensors that are that you get commercially operate in exactly the same manner, because I can imagine little bits of platinum can be very expensive, especially if you're using disposable electrochemical sensors. But this is the fundamental idea behind that reaction and how one of these works. Okay, so I hope that answers your question. It looks like we are getting a lot of other questions that are coming in, and
Bless.
oh, thank you.
Bless.
Oh, sorry. I got we have confirmation. CGM,
continuous glucose monitoring.
Continuous glucose monitoring.
Yeah, thank you, honest.
Yes,
I was not aware of that either. So
someone
knows more about bio things than we do, which is very helpful.
Yeah,
because we are not. I'm not an expert either. So
yeah, but even with continuous glucose monitoring, some continuous glucose monitors.
I mean, it's not a batch process in that case. Is it a flow thing, or I don't know?
No. Wait, for like a glucose sensor.
Well, I'm just saying, like when you say continuous, it makes me think it's like a flow cell. Like maybe I'm thinking wrong.
And they could in a way operate it in a flow cell configuration, or just like collecting data continuously.
Yeah, maybe that's what it is.
I think a lot of I know a lot of glucose monitors are not operating entirely on an electrochemical basis. They're actually doing like spectroscopy and stuff like that.
Wow. Okay, if it's onboard spectroscopy, that's a little different.
Yeah, it's a little different. I think at least. But hopefully that answers your question. And And we can get to some of these
Yeah,
other questions.
we'll
that
try to
have
get
come
to.
up.
I do see there's a bunch here, so let's get cracking
Yes.
and try to get here. So let's see. Shreya has a question. In phase versus frequency, suppose a peak developed in the OCP condition. After hydrogen charging, this peak shifts to higher frequency and narrows down in breadth. What could be the explanation for this?
Trying to understand.
So in the phase versus frequency, okay, let me share, for example, software. I'm going to try to make this happen. If you know what I mean.
Yeah.
Where is
he's going to go into our software
do
to.
I have it open? I don't have it open.
Yeah, so he's going to try to go into our software, and I believe you're going to go into EIS, look at a Bode plot specifically,
Exactly.
and then OCP is just the potential with which the EIS is done about.
Yes.
And looking at the left-hand side,
okay,
if you will,
let me get a circuit simulation.
you'll get.
So let me read it and make sure I got
the phase versus frequency.
So phase versus frequency, a peak is developed at OCP, right? Got it. Okay. And after hydrogen charging, the shift goes to a higher frequency and narrows in breadth. All right, got it. Let's just put a very simple, not Randles, but RC kind of a circuit, right? So look at the blue plot on the left here. This is sort of indicative of what you're talking about. So what I'm gonna do is I'm gonna change some values and I'll show you what one explanation for that could be. So this is a peak right here. You're observing this kind of peak, which is some interface. You don't typically get always a peak in the phase angle plot, for example. I'll just get rid of the other one. So this is the phase angle. Just sort of isolate this to get to the point of your question. Okay. You don't always see, for example, a peak in the phase angle at open circuit, but it does mean most probably that there is a interface, not necessarily a charge transfer process, although possibly a charge transfer process in some regard. It's just typically you have to polarize towards whatever you're doing. Let's just say, okay. So let's just look at practically what happens if the peak shifts to higher frequency. It means that the capacitance is decreasing. So as I increase the capacitance, the phase shift angle moves oppositely, right? So this is one interpretation of that, right? Now you said it narrows. One way to look at that would be by using the alpha parameter. So as I should have started with that, it would have been a little easier to tell. So I'm going to try to, let me perhaps do this. You can kind of see a little bit easier, I guess. So if the peak was very broad and non-ideal, for instance, when you started like this, one interpretation of it is that it became more ideal. You see how it gets sharper of a peak and less broad. And also it's moving in the wrong direction. It's moving more negatively. So to counteract that, I could say the capacitance is decreasing. So in summary here, one possibility to answer your question, just practically based on like values of the components that are at play, is that the phase angle peak moving to higher frequency and becoming more sharp means that it is behaving more like an ideal capacitor with a lower capacitance value. Okay, so that's just one way of looking at that. Now, another is that I can adjust the resistance. It doesn't, again, I'm sort of interpreting language here. Increasing the resistor in this RC will make the peak extend farther down. It's not actually any sharper, but maybe the interpretation in your mind might say, well, look, this is less sharp. This is more sharp. It's actually like the sharpness, if you will, in my opinion, is affected by alpha. That makes it sharper or more broad. But perhaps it's possible that your interpretation of where the peak is based on the resistance being a certain way. So it could be, for example, if the peak gets sharper, the resistance is getting larger, the associated resistance for whatever this process or interface is. So that's another thing. So it could be, for whatever reason, after hydrogen charging, that the resistance impedance is going up slightly, and that's causing the peak to get whatever. That won't change its position, right? So you would probably say something like it's a coupled effect of a decrease in the capacitance with an increase in the resistance. Okay. So in summary, it's like, I can't answer why per se. Like you have some material, you've charged it with hydrogen. I would have to. I don't know if I can answer perfectly well. Like, why does charging with hydrogen lead to that? Like, obviously, something about the morphology, something about I don't know, XYZ property of your material after charging with hydrogen, or this process that you've done has led to potentially, I would say, a higher resistance, higher impedance, um, which might be a degradation of some sort. I don't know. Hydrogen can cause like cracking in structures. Maybe that's what it is. Just a guess. Or again, it is has a lower capacitance. So again, I don't really even know how or why. These are some of the things you might be able to explain with your more thorough knowledge, presumably, of your material. Why is the capacitance changing, and why is it more ideal or less ideal? Things like that. But those are the sort of practical, I guess, mathematical parameter reasons why I can show you how that Bode plot, phase angle peak will move. So hopefully that's like a set of things for which you can try to figure out how it relates to your catalyst, and one of those things might be applicable. That's the best I can tell you without more information about the exact catalyst, of course, and knowing your system, which I obviously don't know your system intimately. It's your research and your catalysts, but hopefully that gives you some direction.
So there was a question from Fernando. I think we may need a little bit more clarification, but he says, "Hello, I'm working on a quasi-reference electrode. I expect a potential shift. I use an alternative to silver chloride, but I didn't anticipate a twofold increase in current. Any insights on this phenomenon?" So when you say a twofold increase in current, I'm assuming you're doing some cyclic voltammetry, and you normally get a regular peak. And when you change the reference electrode, you would just expect a shift in that same peak. But now you're saying that instead of just getting a shift, you're also seeing that the current is doubled on your in your CV. So I just want to kind of clarify what you mean by twofold increase in the current. Um, and Fernando, please let us know, because you're right. I think it is odd that you would have a quasi-reference electrode and experience current changes, unless something else is happening. But
I mean, it's like there's nothing fundamental, I would say, I guess,
mhm,
about a reference electrode that's going to do that. Like,
correct.
if if what you're talking about, I think that's kind of the point that you're making
Hmm.
here too. It's like, if the potentials are adjusted and you know what potential is correlative with the previous experiments, the reference electrode is not going to do anything to your current, or the potential axis will shift, but the current will not. So
Hmm.
it might be perhaps that your perceived twofold increase, or just any change, like beyond experimental error in the current, is because you're at a different potential entirely. You know what I mean? Like
Like
you're
another process is happening.
yeah, what you think is the same peak or process is shifted by so many millivolts or whatever,
Hmm.
that it's like, well, why is the current here so much higher? Maybe you're doing bulk electrolysis, for instance, and the current is higher, and it's like, well, that's because it's like it's the equivalent of applying, like before, you were applying 400 millivolts, and now you're in some different pseudo reference, and you're applying like, what you think is the same, like versus NHE, like corrected, but
Hmm.
it's actually like you're applying 700 millivolts. So it's like, well, the current
Yeah.
is different because now you're doing more oxygen evolution, or, like your perception of the potential you're at is incorrect, is my guess, because there's nothing about a different reference electrode that will lead to a different, like, it's almost nothing that makes any sense that it could. It's not how a potentiostat works. So
Mhm.
probably that you are not necessarily applying the same potentials, um, that you believe you are, for one reason or another, is my guess.
So he says exactly that, but I
Yeah,
forgot
I
what
forgot. Well, yeah, I was gonna say I
which
don't
one of
remember
those
which
which
exactly thing we were.
exactly
Yeah,
thing we
exactly.
were
What
talking about.
exactly what?
One other thing or comment. I mean, if it's the cyclic voltammogram peaks, and you are getting, in fact, these two peaks, and it's double in current, something else has to be happening.
Yeah.
The only other thing I would say is if you're doing like hydrogen evolution, where you tend to see like, an exponential increase in the current as you change the potential, kind of like Butler-Volmer kinetics,
Yeah.
then even a little change in the applied voltage will create a huge change in the measured current, especially when you're at that limit. That's the other thing,
That's a
only
good
other
point.
thing. So unless it's a CV with like, I would say well-defined parameters, like you've swept sufficiently positive or sufficiently negative that your redox peak is kind of in the middle, then shifting the potential, like unless you shift it so much so that it's cutting off part of where the CV is forming, that's the only reason you'd see like a twofold difference in the current, is you're not applying enough of a potential, or you're shifting it that far away. But it's got to be like, let's see, so it's double the peak height. Let's see. So he says it is double the peak height.
Square
Okay.
wave.
Square wave voltammetry and metal detection stripping. In metal detection with anodic stripping.
Yeah, I
So
just
square
suspect that
wave.
there's a mismatch in the potentials that you think you're at. They're not comparative, especially if you're doing square wave because it's subtractive. So you're actually not observing the raw signals. You're observing a differential current in square wave. So what it is even going to make it harder. For example, like just for instance,
Well, if he's doing anodic stripping, is the peak is in the square wave, not in the anodic stripping?
I believe so.
Because if it's in the anodic stripping,
All I'm thinking is that
you're
just like, for example, if you do your first one and you have like,
mhm.
you have your CV or whatever, and then it's like you do it again, and what it sounds like, I should draw this sort of like, let me draw it a little differently so I have a little more space. So it's like, let's say this is your CV, and it's like you have oxygen evolution. If you go to, this isn't your exact, you know, system, maybe, Fernando. So pardon the.
Yeah.
I'm just trying to think of an example of as to what I mean by your potential isn't where you think it is. So it's like then you do again, and it sounds like what you're saying is that you're getting basically this or whatever, but it's like this is assuming that this potential is lined up exactly perfectly. And what it sounds like to me is that you were basically observing like a peak over or a current over here, right? Which would correlate to but it's like your potential's wrong. You know what I mean? So it's like it would be the equivalent of doing your CV over here and saying, well, why is my current, this high? But it's like, because you're at like 800 millivolts over here and you're supposed to be at 400, but you think you're at 400, but you're really at 800. Like it's a misperception of where you're actually at. And then because if you're doing a square wave is a subtractive technique where you're going like this with the potential, right? And you're taking this current, subtracting this current. So if you have like some process going, you're always subtracting this from this, this from this from this. So as you shift the whole potential left or right, because your pseudo reference electrode, whatever, it's like the peaks might not be correlating to exactly the same thing anymore. Like again, it's a perceived potential difference. And then the problem with square wave is that you're not even looking at the raw signals. You're looking at a subtract. This is like subtracted current, right? Or differential current, whatever that you're looking at with square wave voltammetry. So you're not even in a situation where you might be able to observe two distinct CVs with the same peak and whatever to say like, oh, well, it's clearly not in the same position. So I don't know if that kind of helps clarify that a little more. That's what I see here. I don't know if you have any other sort of comments before we move on. I think it's a potential issue.
I think I feel like there's something else that might be going on,
Yeah,
especially when like if you're doing square wave, you're probably doing something very sensitive. You might be looking at microamps of current, like even single microamps, where sneezing could cause like doubling
Sneezing
or something. Yeah,
yes.
just some of the I feel, and like working electrodes are so finicky, right? Working electrodes are just super finicky. So even though like this is something where it's like we actually have to see the entire, I feel like we'd have to see the whole experiment, get all the parameters and actually see it, because you know, Neil and I have troubleshot a lot of electrochemistry problems, and sometimes, you know, when someone, especially in just a comment on YouTube, and then we're not saying like, Fernando, you didn't give us enough details and blah blah blah. Bad. It's more like we assume when we see like, oh, I only changed the pseudo reference, we assume nothing else changed, like absolutely nothing else changed. But sometimes it's often the case that there is some tiny little change, like even like how many scans you've done, or a parameter that was maybe adjusted, or um unless like the amplitude or something changed in like your square wave, maybe that played a role. I don't know, but yeah, I don't know. I'd have to look a little bit. I think we'd have to look a little bit closer. But
Yeah. I think
anyway, we do have a lot of questions.
we'll
We'll
move on for
hopefully
now.
get
Yeah,
to,
for
yeah.
sure.
So Sam Murphy is asking, can you discuss the effect of electrode polarization and quantifying the permittivity, or penetration depth of the field felt by the active mass? Um, so what I think you're talking about when you are asking this question is and
It's becoming your new favorite diagram.
yeah. Oh
You've shown
yeah.
this like you've shown this a lot actually. It's
Yeah.
becoming your new. I'm thinking it's like rivaling the Nernst
It's
equation.
rivaling the Nernst equation, or one of the. Hopefully, you guys can see
Yeah,
this.
we can see it. Yeah.
So, I
Okay.
think this is what you're talking about. And Neil, even clarify if you even interpret it
This is
differently.
this is the
This
first
is
thing that came to mind because I work with you and
Yes.
you've been showing me this this plot for like a year and a half now, so I have it ingrained in my memory. So
I have been staring at this plot and these numbers for so long, like, because sometimes we say like, I mean, Sam, to your point, it's just like, I polarized the electrode by like 1 volt. What does that actually mean? Like, we talk about electric fields, like that's what a voltage is in a way. We're using that to describe the electric field strength. So, so Sam, clarify with me if this is what you're talking about. But this plot on the right hand side is from Electrochemical Methods, Fundamentals, Applications, 3rd edition, Barden Faulkner. And I have to figure out exactly what page this is on. But what this plot shows is the potential difference at the electrode surface. So this is the working electrode as we come to picture it. You have an electrode. I've polarized it positively. So this is as if I was applying a positive potential. And then we form the electrical double layer, the inner Helmholtz plane, outer Helmholtz plane, and diffuse layer. And this plot on the right-hand side shows the potential of the phase of the metal and the potential of the phase of the solution, which is S and this is M. And this is distance from the electrode electrolyte interface. So everything here is solution. Everything here, negative X, is metal. So when you have a supporting electrolyte of sufficiently high concentration, you end up getting, you see the potential drop off looks something like this. It goes from here all the way to here before it's basically the same. And X1's the inner Helmholtz plane. That's like 1 angstrom, like half an angstrom, right? It's the center of like an ion, right? From the center of an ion to the surface. So it's really, really short. Similarly, the outer Helmholtz plane, also equally not very far. And then there's this diffuse layer, which is not a well characterized zone, but it's like you feel a strength, you feel a field strength, and then it's as if you were in the bulk solution. So this change in potential is usually quite large, but the field strength is contained to a very small area. And so when you talk about, let me just go back to the question. So I think what you're talking about is this like penetration depth. What is the field felt by the active mass? So only when the active mass is in this area is it going to feel the field strength. And so that's a very small or short area. And I can't actually comment very much on permittivity. or at least quantifying it. This is just something I don't know that much about. But when it comes to electron transfer, it needs to be in this range. It's only within like 10 to 20 angstroms that an electron will be able to feel the field strength and then gain or lose an electron based on this difference. So that's my that's my brief discussion, sort of say, of the effect of of electrode polarization. This is the kind of field strength graph that you end up getting. Uh, Close it. So hopefully that answers your question. Let's see. Let me see. He has a follow up. Yes, for the most part. I'm wondering about the connection between the degree of electrode active mass utilization and degree of polarization.
I think it's like if you polarize the electrode more, is more mass of the electrode like involved. We talked about this recently with respect to semiconductors with the
Yes.
band bending.
Yeah.
So I think the short answer would be yes for semiconductors, probably no for conductors, or at least not like all of the mobility, electron transfer, of a metal, a conductive like metal or whatever, is in the conduction band and is at the surface of that electrode.
Mhm.
It is generally, for a solid material, not considered the case. I believe, where like you have a lot of like penetration into the material of like but it's also, I don't know if this is the right answer, because you said like like utilization, like for
Mass
what, right? Like
utilization.
is it just, can something penetrate? Well, obviously sometimes ions or things can penetrate into metals, into the mass of a material, so that can happen. And then again, like what we were talking about the other day, for instance, was like this idea about the band bends, like for a Mott-Schottky test in a semiconductor, as you change the polarization, as you change the potential, basically, it's like the energy level. It's like you're stealing from the valence band or whatever, or something like that internally. So it's like I don't know if that's the same principle where it's like utilizing more of the mass of the thing, or if that's analogous to what Sam is asking. That's kind of my interpretation of that question.
Yeah, there's one way to think about it for pure electrodes, for pure conducting electrodes. This is a thing Neil and I have talked about before. The difference between a conductor and a semiconductor, one aspect of the difference is that conductors. Wait, hold on. He has another thing. So he's saying like active material utilization for capacity in NMC and do you know what these acronyms?
Those are battery cathodes.
Those are battery cathodes. Okay, so he's talking about like the mass.
I don't think
capacity.
That the polarization is going to make much of an impact on that. I think that when you have a material, this is why I paused when I started talking about how, no, it doesn't, like it's at the surface, but the exception is a thing like a battery electrode, which is to say, when you have a battery electrode, it does have like mass utilization is a weird phrase. Like I haven't seen that used much.
Yeah.
Maybe it's more ubiquitous than I'm aware of, but for lack of any other wording, when you have like, let's just say 20 microns, 100 microns thick, cathode or anode layer in a battery, it's like, yeah, all of it will get intercalated or deintercalated, can be used. The degree to which you polarize isn't necessarily going to change how much of the thickness of that material will be like used. It might change the speed or the rate at which it is charged or discharged. So like, for example, if you have a cathode material that's 100 microns thick and you're polarizing it, so you're charging it or discharging it, in which case, if you're charging it, you're removing lithium from it. If you're discharging it, you're adding lithium to it. Let's just say you're adding lithium to it. It's like lithium people have done in situ like visualization, like microscopy of this, where you can watch it's visualized with a color change. Like you can watch, like for example, like with the anode, it's a little more obvious. It's like the anode's graphite. It's usually it's black, and as lithium goes in it, either they do it, like after the fact with a EDS like elemental change, and you can colorize what element you see by what, so something like that. So you can watch it like, and the line moves from the front back as it gets lithiated, but it goes from the front to the back. And so there's like more mass utilization, so to speak, as time goes on. But it's like, it's not necessarily because the polarization is so big. It's just, this is just a matter of like, how fast are you charging it or discharging it, right? So it's like that inner portion of the mass will be utilized regardless. It's just, it's going to take longer if you're polarizing it very minimally. Does that make sense? That's kind of how I would describe that. I don't think that it's necessarily that a small polarization, which would be a way of saying I'm charging it very, very slowly or discharging it very slowly, means I'm not utilizing part of the cathode material or the anode material. It just means it's going to take a longer time. That's why you're charging slowly. So that's how I would answer that.
Yeah, I think that's a good answer. We have a next question by Tania1. Do you need to fit every peak identified by DRT calculations in circuit fitting for impedance data? I often see multiple processes in via DRT, but the Nyquist plot is mostly just a semicircle with a Warburg.
So you can, the problem is going to be that if you try to fit every DRT peak with an accompanying RC, and the EIS data is let's just say let's just make it simple, right? Let's say you get 2 DRT peaks, and on the Nyquist plot, it looks like one semicircle. So the DRT is telling you that there are just 2 distinct time constant processes occurring. But this is why you do DRT, because you suspected there might be, but the Nyquist plot is showing one semicircle effectively. The reason for that is that either the capacitances or the time constants for those processes are too close. They're very, very close together. This is why DRT is valuable in a place where circuit fitting is not. You can fit 2 RCs to that one semicircle. The problem is you have an almost infinite number of possible solutions, because it's not unique. You will not have necessarily a unique solution for each semicircle from the circuit fitting. This is where DRT is valuable, because it allows you to get distinguished, quantitative to a certain extent, results on multiple processes occurring at different time scales, but very close time scales. The circuit fitting will not. You will very possibly end up in a situation like, just as an example. I'll show you again in our software here. I'll kind of give you a very rudimentary example, just as something here. Let me pull up a thing. All right. So let's say I'm going to neglect the Warburg for a minute, and you shouldn't be fitting Warburg with DRT anyway. So don't do that. Okay. So here is, for example, two semicircles, right? Okay. Well, what the DRT is telling is a situation where I have like one semicircle, or let's just say like it's sort of 2. So I'm changing the capacitance values very slightly, but you can barely tell, right? Oh, that's the wrong one. I want to change these 2. So changing the resistance is like, oh, look, you can kind of tell a little bit of inflection, but it's like it's almost impossible to tell the difference. And so when your time constants are really, really close together, like I'm showing them almost identical here, DRT might show you 2 peaks. And so that's why it's useful. But what I have is a basically infinite set of values. So if this one is 1,000 and this one is 1,000, it's basically like I have 2,000. Let me make this 0 just for argument's sake. So this is what my Nyquist plot shows me. I have a width of about 2,000. Okay. I could have 2 RCs, and I might do my fit and say, that means that the first charge transfer process has 1,000 ohms and the second one has 1,000. Okay. Another possibility is I can make this 500 and this 1500. It's the same thing. Now there's maybe an ever so slight inflection here. Kind of can't tell, but it's the same, basically the same result, right? I still have 2000 overall. It's like ever so slightly inflection, but it's going to be hard to really capture that. It depends on how close the DRT peaks are. In other words, what I'm showing you is I just did two different possibilities, both at 1000, one at 500, 1500. Like I could do this all day. I could do 100 and 1900. I could do 200 and 18. Like any set of resistances. Now it'll change this inflection ever so slightly. Maybe that's enough to do to get results circuit fitting, but I suspect it will probably be very difficult to get accurate results. And it means that these two sets of values can be almost anything, and the end result will be roughly the same. Okay, depending on how close your DRT peaks are. Is that there's almost an infinite set of resistor values. And so you won't be able to, like, with confidence say, well, my DRT says there's two processes. And when I do the circuit fit, I use two RCs, and I fit them, and I got this much ohms of charge resistors, and this is the second ohm. It's like, yeah, but it could be any two numbers and it would fit the same. So when you don't have the uniqueness of it with circuit fitting, that's where DRT comes in handy. Okay. So you can try. There's a strong chance you might not have very much success, let's just say, in differentiating between those two processes.
Nice. All right. Next question. This is actually related to our software. An Aftermath Blue version. I can't do EIS circuit fitting on my personal laptop. Every time I do in the workshop, I can only can Pine solve this issue. So perhaps send us an email about this. It might be like a technical troubleshooting.
Well, I'm pretty sure I know what the problem is.
Oh, yeah,
So Shrajib, what you have here is if you have Aftermath Blue and you have a Pine potentiostat, the EIS potentiostat is the dongle for the circuit fitting. So I think that's what you're saying, is that you have to sit in the workstation and do it. So one way to get around this, because I understand you want to do circuit fitting sort of on your own, is to connect your computer to the workstation with Aftermath open, and then you can do circuit fitting, right? And you can do it. If you disconnect your computer from the potentiostat and don't close Aftermath, you can still do circuit fitting. It will, like, remember the instrument was like enabling circuit fitting. It's like the dongle. If you just don't close Aftermath, so I know that means you have to keep your computer on, but I don't know, a lot of people don't turn their computers off all the time. So you can take your computer home as long as Aftermath is still open. Take your computer anywhere else. Try it. Like take your computer here, plug the instrument in, try circuit fitting, and it'll work. Unplug the instrument, take your computer over like 2 meters to the lab bench, and then try to do circuit fitting. It should still work because it remembers. But if you close the software and then reopen it, it won't remember. So you have to keep the software open. That's kind of a way around this, because we have moved to circuit fitting licenses where you can purchase them, and the instrument is the enabling. If you have an EIS potentiostat, then it enables you to do impedance as well. And so that's a way for you to do it if you don't have the ability to connect to the potentiostat. Just make sure you've connected at one point and then don't close Aftermath Blue. Keep it open. Mm-hmm. Hopefully that'll be possible for you. If not, contact us and we can try to work something out. We do have licenses for circuit fitting. As I said, we normally sell them for purchase, but we might be able to work something out. So.
And he has a second question, which is to explain GITT and PITT.
Explain GITT and PITT. So GITT and PITT. GITT is galvanostatic intermittent titration technique, and PITT is potentiostatic intermittent titration technique. So text box, I'm not going to write these words. That would be a disaster. GITT is galvanostatic intermittent titration technique. So GITT is a technique where you alternate applying a constant current and applying nothing, doing open circuit potential. So let me think Red is usually current. All right. So it's a double axis plot type of a thing when you're all said and done. We have current over here. We have time over here. If the question's blocking it, you can move it. I'm not sure.
No, it's still good.
Okay. And we have potential over here. Okay. And so the procedure involved is where we have, let's say this is 0 right here. And let's say it's usually a battery. So let's just say this is like 3 volts and this is 4 volts, usually, between charging and discharging a battery. I should actually draw 0 somewhere more in the middle. Okay. So what you do is you are alternating applying a current, then applying 0 current, then applying a current, then applying 0 current, then applying a current, applying 0. So that's how you charge it up. And then you could discharge it by applying a negative current, then 0 current, and then negative, and then 0, right? So it's pulsing. Each of these pulses is usually about 15 minutes. So it's not quick, but it's not, but there are breaks. So it's maybe 15-minute like intervals, 10 minutes, 30 minutes. It varies, but that's usually the time scale, roughly speaking, is about 15 minutes at a time, give or take. Okay. And then the potential responds accordingly. So if you're charging it up, you might have like charging and then open circuit and it settles out for a bit and then it charges up a little more and then it settles out, open circuit, and then you're charging it up a little more. And then I drew that too far. I'm trying to line up with the red lines here. And then charging it up some more and then open circuit. And then you're going to discharge it. And so then it goes down and then the open circuit takes over and then you're discharging it some more. It's a charge discharge kind of experiment, but in pieces. So that would be the last OCP. That is GITT. Here's an example of GITT. And I'm going to pull it up. This one. So this is some data, some GITT data, just to show you as an example. It's just kind of what I drew. It's just spread out. So it's a lot smaller here. There's a lot more data. You can see the current is the red on the x-axis here. If I zoom in a little bit, you can see this one's a bit weird. It's like a lot of charging and almost no OCP, but there was like a short step. So I had like, in this case, I don't even know how long this is in hours. So like 1/10 of an hour. So like what, 10 minutes, 6 minutes, and then like 10 seconds of OCP. So yeah, I mean, it varies exactly how it works, but you can, the specifics here, but you can see this is the potential axis. So I applied a negative current for a while here, and the potential started to drop. And then OCP, the potential sort of recovers. And then I do another pulse to keep going down, keep applying negative current for a while, and we just do that forever and ever until it hits a lower limit. And then I switched the direction and I started applying a positive current with some intermittent OCP until it reaches a positive. So it's like a charging, discharging kind of experiment with potential limits. And that's how that works. PITT is the exact opposite. So I'll come back here and explain PITT for you. So PITT, perhaps, obviously, if you just learned about GITT, PITT is potentiostatic intermittent titration technique. And PITT is where instead of controlling the current, we're controlling the potential. So it's the exact same phenomena. We have time over here. We have current over here. Let's just say this is 0. And we have potential over here. Let's say this is 3 volts. And that's 4 volts. Okay, great. So what we do now is we apply, let's say we're starting at 3 volts, let's just say, right? So we're going to apply slightly higher voltage or whatever, and then OCP. And then we're going to apply slightly more volts, and then we're going to do OCP. And then we're going to apply more. So we're applying increasing steps of voltage and then we might step back down and step the voltage back down, and sometimes it recovers. And so all of the curved lines are the OCP, all of the other ones are steps of it. And so as you're stepping the voltage up, you'll get a decay of the current, and then at OCP the current is 0, and then you'll get a decay of the current, some amount of current out of it. The current is no longer constant. Before, the current was constant. Now the voltage is constant. And so as you step higher and higher, sometimes the current gets higher and higher. Sometimes it'll be about the same. Current starts to decay, and then you go the other way. And so you might have the current decay the other direction, and then 0. And then the current decays more, and then 0. So that's a pit. So the constant one is now, instead of here where the current was constant and the voltage responds, this one, the voltage is constant stepped and the current responds. That's pit, and this is an example of pit.
Nice. Oh, you have an example of pit?
I have an example of pit. Yeah, I was just going to show it. It's look. I mean, it looks almost the same. It's hard to tell the difference at a quick glance, but you can see the red lines now are the current, and so those are the ones responding to the voltage. So each voltage plateau here corresponds with the current decaying a bit, and then everything goes to OCP, and you just step the potential down and down and down and down and down forever until you reach wherever you're going, and then you go back, and that's pit.
That's pit.
There you go. So that's, that's pit and GITT. All right. I explained pit and GITT. There you go.
Very good. Going down the list, we do have quite a few questions. This is unusual in a way, which is good. Noobmaster69, how do you do you understand cysteine's functionalization on gold and its relationship to EIS? I don't think either of us have studied it specifically, but I believe cysteine has a sulfur group on it as an amino acid, and it usually forms a sulfur gold bond based on hard soft. Not acid base. Maybe it's acid base. Hard soft bonding, and so they functionalize on the surface, and then you can do EIS, and you'll have like a monolayer of some cysteine or something on the gold, and maybe get some EIS result.
I'm guessing it's as simple as, run impedance before and after functionalization, and you'll see a difference. Most probably you'll see a difference in the, if it makes a layer that's substantial enough, there will be an interface between the gold and the cysteine layer. That layer is called the cysteine chapel. Sorry, I couldn't help it. That layer could cause an interface, which could manifest itself as a semicircle, maybe a small one. If the bonding is so tight that it's almost like the layer is so tightly, the functionalization or so is so tight, maybe it won't manifest itself as a semicircle, but you might get like a diminished resistance or a change in the capacitive behavior because now you have functionalization on the surface. So I just suspect that as you do this, you should be able to observe differences in the impedance, but it's exactly what those look like, I don't know. I haven't done that experiment.
Moving on, Chris Z is asking, which working electrode is the best for water splitting reactions? Probably platinum.
Platinum, palladium, ruthenium. Different. It's usually noble metals, and a lot of times it's alloys of them. I think ruthenium and palladium are some of the best, if I'm not mistaken. But typically for electrolyzers and things of that nature, people use platinum on carbon, ruthenium, palladium, and maybe gold. I don't know, but it's because they're noble metals and they're generally unaffected by the high potentials required to do water splitting, I believe. So,
All right, moving on. Of course, if you have further questions and clarifications, please let us know. We do see we have a bunch of questions. We have someone from X who we will eventually get to, but we are working our way there. We're working our way there. Lev asks, I have nickel plated on thin porous palladium. It can be represented as two parallel Randles circuits. I'm afraid that response will look like for a single Randles circuit where nickel and palladium are not separated. Is it possible to study porosity of such kind of electrode by EIS?
Yeah, so you would want to do something like a transmission line fit. Transmission lines are typically used for the calculation of porous electrodes. I did a webinar once using transmission line. I want to pull it up real quick here. I was actually looking more at tortuosity, which is not the same as porosity, but it's a similar phenomenon. Let me just pull up these slides real quick here. So it's the depth related to. Okay, so this is the best that I can kind of answer for you, because probably the answer is yes, and specifically I don't 100% know, but this is the best knowledge that I have of it myself. So, for example, porous electrodes can often be fit with what's called a transmission line. It looks like this. It's a sort of an infinite sum. It's used for pores, electrodes with microporous structures, and it helps to define situations where you have a charge distribution within the pore, and so it's a sort of this infinite sum. And mathematically, you can do this. This was done where I took from a paper where they used this circuit fitting procedure to calculate what's called tortuosity, which, as you can see, that's like the difference between the straight line between 2 points and the path through all of the pores if there's a porous structure. So it's not porosity exactly, but you can see it's kind of similar. And so they're at least related, and it uses this what's called the McMullen number. So tortuosity divided by I think this is porosity here is. So there's it involves the use of this resistance here, the surface area, I guess the diameter of the pores, if you know that, and then what the heck is K? I don't even remember. It's been a while since I've done this, so my apologies that I'm a little bit rusty on this information here. What is K? Is it's conductivity, I guess. So in any case, this you can see this paper here. I'll just kind of put it in. This is an interesting paper. You can find this source if you'd like, where I'm getting this information from. But it allowed, it was a way for them to calculate the McMullen number from resistance measurements using a transmission line fit, which is available in our software. Some other software platforms might have it as well. It's something that you can do in Pine and Aftermath Blue. I guess I'll show you that too. Why not? When you have data that you can fit with that. Now, the tricky thing is whether your data appear in this sort of a format here. So this is where you can fit, for instance, this sort of model, and you can change the elements as you need to, the boundaries and the inner parts and everything, and then simulate a transmission line. So if your data looks something like this, you might work. So it varies. This is just one example. Usually you have a sort of a tail at the high frequency instead of the low frequency. It's almost like the Warburg happens first. It's kind of a way to think about it, like oddly. It's a bit of a weird thing. If you're not used to seeing this kind of model, you might not know exactly what you're looking at. It might take some time to get used to. But in any case, you're looking for usually the top resistor here, this resistance, or the resistance across the pore, something like that. And you can correlate that. Again, read the paper. They kind of describe it a little bit better. And that might be a way for you to do that. That's the best that I can tell you in that regard. Otherwise, there might be other ways, and you might be able to find a paper where you could, I don't know, maybe they correlate the capacitance somehow, because capacitance is proportionate to surface area. So there might be something there. I just don't know specifically if you can get a numerical answer for porosity exactly from impedance results. I don't know offhand. I have to look into the literature a little bit more.
All right. Next question is from Anonymous Wombat. Anonymous Wombat asks,
It's my favorite kind of wombat.
the anonymous one.
That's right.
Can you explain what charge transfer in batteries is, and if you see it in experimental EIS? This is just
So charge transfer in batteries is the process of adding or taking away an ion from the anode or the cathode. So
so you've shown some. I know you've drawn like reactions.
yeah,
There are multiple forms of charge transfer for batteries, though.
yeah, for sure. But I mean, I guess I'd say the simplest, like if you're looking at an anode and a cathode of a lithium ion, because that's the one that I'm most knowledgeable about, I guess.
Yeah.
This is carbon, is C6, and so the reaction is this. So this is the charging reaction at the anode of a lithium-ion battery, and so the charge. What was the question specifically? Can you explain charge transfer in batteries? I mean, that's the charge transfer, and then the cathode. If the cathode is lithium, during charging, lithium dissolves basically, or oxidizes, and you get lithium ions. So the charge transfer is just the processes by which, and then this is charging, and so discharging is just the opposite reactions. So the charge transfer in batteries is just these processes, these Faradaic reactions where there's other ones of the SEI formation or whatever, but let's just simplify it and say these are the main charge transfer processes. And then in an EIS, batteries are odd. Sometimes you get different sorts of things, but you often get something like, sometimes you get two semicircles, and usually this is the first semicircle is related to the SEI or the anode. The second semicircle is the cathode, and then you have like Warburg diffusion. So the charge transfer usually of the cathode is correlated with this semicircle width, if you will. And then the charge transfer resistance, so this would be like the R of the anode, and this would be the R of the cathode. So roughly speaking, impedance tends to, it depends, and doesn't always look like this. Sometimes they mix together. Sometimes it depends on the state of charge of the battery. If you get two semicircles, if you get three, if you get one, it varies. But generally speaking, it's something like this, that the resistance of each of these processes manifests on a Nyquist plot like this, and the widths of these semicircles correlates to the charge transfer resistance of each of those processes.
Mm-hmm. Hopefully that answers your question about what is charge transfer in batteries. I think it's also important to at least mention that the lithium has to intercalate into the carbon.
Yep.
It's not like a traditional electrochemistry reaction that's just happens on the surface. It literally has to go into the carbon to, in this case, lose an electron. And then the electron then goes to the circuit, does the work, which is why we want to have batteries, and then flows out on the other side where the lithium is oxidized, as Neil said. So let us know if you need more clarification on that. Next question here is from DF. Hi, can you explain the basics of charge transfer in polarizable electrodes like platinum? How does a voltage cause a redox at the interface if the electrode is inert? So, in general, basically, I don't know. This kind of gets into like fundamental electrochemistry.
Yeah.
For
Also,
the
the
most part.
word inert is probably tripping you up.
Yeah,
It
yeah,
doesn't mean it doesn't do anything. It means it
yeah,
doesn't fundamentally change while functioning as an electrode.
yeah, yeah.
Right? The word inert makes it sound like it's just sitting there, like I'm not here.
Yeah,
It's
yeah.
like, that's not what we mean. When
And
we
in the
say
case
inert.
of platinum, it's actually quite the opposite because platinum's very active.
Yeah,
That's
exactly.
actually a
I
very
used to take
catalytic
umbrage
material.
at using that term. I've kind of gone and
You-
join the cult. I used to, do you remember? I used to be very irritated at using that word.
Oh, I
with
do.
platinum.
But there's much more things you found irritation in.
That's
So
correct.
I think
I'm a very ornery person, so I find other things to be irritated about. But I used to have the same, just for what it's worth, DF. I used to have the same, like, why are we using this word inert? It doesn't make any sense. Platinum does all these things.
Yeah.
You know, it's
Yeah.
really like, it's even the CV of platinum has a million different features and peaks. It's like, what?
That's true.
Inert would mean to me that it's just like a flat line, nothing's happening. It's just,
Yeah.
it's just understanding what we mean when we say inert. That's all. It doesn't mean that it doesn't participate or do anything. It just means that it's relatively unchanged and
Yeah.
great at doing catalysis, because you can cycle it, you can catalyze reactions, you can do all kinds of stuff. And at the end of the day, it's basically unchanged.
Yeah.
That's what
Yeah.
we mean.
So the basics of electron transfer, I'll just go back to, I guess, a slide if I still have it. So I think I shared this before, but like
It's the picture of my dreams.
the picture of your dreams. So you have an electrode. If this electrode's platinum and you're in some electrolyte with redox species and stuff like that, you when you polarize an electrode, you're building up charge at the electrode interface. This charge only shows up when negative charge it comes to balance it out. So if you didn't have any supporting electrolyte, you would form no potential at your electrode surface. So I think that's an important thing to recognize. Like you couldn't, you couldn't put an insulator, you couldn't put a piece of wood in salt water and then have these electrochemical reactions occur. You need charge, and similarly, if you just put an electrode in toluene, pure toluene, just organic solvent, no charge, you will not form a potential. Of course, unless there is impurities, charged impurities in your toluene. So the potential would not form. So this potential interface between the positive and negative charge, that voltage difference, I like to think of it as what we call like a Fermi level. So you can think about, and actually I draw this in another part, but like this is energy, and these are like filled electrons in the band structure of your electrode. And so the potential is just the energy of this thing. And then when you have redox molecules, when you have like oxygen, O, and it's being converted to R, the potential, and so actually let me delete these so that it's easy to see. You get electron transfer when the energy level, when there's like an energy level, like let's say if you're doing like a reduction reaction, then it's the highest unoccupied orbital. You'll get an electron to move into the orbital. So this is what we call like the HOMO, highest
Highest occupied.
highest occupied.
Yeah.
So now I need the LUMO actually.
I can never say those right. It's always like lowest
lowest
unoccupied,
unoccupied.
highest occupied. Yeah, yeah.
Yeah, so it's like the LUMO.
Yeah.
And then you can get an electron to transfer into here when they're the same energy level. And so when you adjust the potential and you polarize it, you're moving this entire band structure up and down, which is also to say you're changing the amount of charge at the electrolyte interface until it matches the LUMO of a redox active molecule. That's when you can get an electron transfer to occur. And then this is like the structure. And then my favorite picture of all time now is when there's a molecule where where it's in this range and it's feeling the field strength. Is it able to undergo an electron transfer at the electrode surface?
We need to let our molecules feel their feelings.
Yes, exactly.
It's like a therapy session for molecules.
Yeah.
They can feel their feelings. They can feel the strength.
Yeah.
Feel the field strength.
They need to feel the field strength.
Right.
It's sufficiently high enough field strength so that it can undergo an electron transfer. So hopefully, DF, that answers your question. Of course, if you need further clarification or you want to know more, please let us know.
Ryan, welcome back. You asked this question last week. I didn't forget about you. And I think I visited you at University of New Hampshire At this point, it was probably 2 weeks ago.
We'll
You wondered
answer
if
both
we
those
could talk
questions.
about moles transfer during a reaction in cyclic voltammogram. So that was the question last week, and now it's you're back asking identify regions or features on the Bode plot. Do you want? I mean, the moles transferred during a cyclic voltammogram, probably just looking at Faraday's law, electrolysis, or something like that.
Or you can just look at the current versus time, removing background current, and then
it's then
getting
Faraday's
the area
law.
under the curve.
Yeah. So okay.
So there's two ways.
Let me try to answer that one first, I guess.
Yeah.
So we can look at this as moles transfer during. So if you have a cyclic voltammogram, right? Let's just say it looks like this, and this is current versus voltage. Okay. So let's pretend instead we're looking at just the current versus time portion of it. And so what we're going to do is over time, we have that, and then we're not going to draw the backwards wave. So like just the current versus time part. So this is the like first part of the CV, right? What we would do, for instance, is if this is 0 right here, this is like a perfect example. So, maybe everything doesn't look this perfect.
Mm-hmm.
This right here would be like the background current. So we would want to subtract this out. This is the background. This is like the charging of the double layer. Okay. And so we would just have to just make some assumptions here. Let's just pick here, right? So let's just say all of this area right here, this is the area under the curve. And this is like the integration. That's a backwards integral. I'm so good at math. The backwards integral of I dt, basically, from just, I don't know, T1 to T2, whatever.
Mm-hmm.
So let's just call this T1 and this be T2. So we're integrating, and then we're subtracting background right there. I'm just making this that we're subtracting all of this crap. I'm just trying to make it simple without doing all this math for you. The point is the integration of this is the area under the curve. And so what that's going to give you I dt here, it gives you coulombs, right? It's just 100 coulombs, whatever. It's some amount of charge. Okay. And then what you need to know is the stoichiometry of your reaction, for instance. So if you have A plus electron goes to B, whatever, then it's just a simple bit of mathematics. So I'm going to keep changing the colors here. So it's like a very fancy slide. So you'd say I have 100 coulombs, and then you're going to use Faraday's constant. There's 96,485 coulombs per 1 mole of electrons. This is that right there is F. That's Faraday's constant. So it's just a direct conversion. Moles of electrons per coulomb. And then my stoichiometry says that I have 1 mole of electron per 1 mole of, I don't know, whatever B. That's a terrible B.
It's all good.
Man, drawing is hard sometimes.
Drawing is hard I'm
just not a great artist. And somehow
PowerPoint.
Drawing letters is hard. Yeah, on PowerPoint, it's not the easiest.
Yeah,
All right, so we're just using the stoichiometry, 1 mole of B, electron to 1 mole of B, whatever your stoichiometry is. And then, whatever B is has X grams per mole. I guess you asked for moles. So if you want to get grams, you can get grams. You can use formula. You don't have to use this part. But this basically gives you this many coulombs converted stoichiometrically to moles gives you how many moles or grams of product or whatever was made. And there's assumptions here. You're assuming that all of this, you really took out the background appropriately, and there's no other reactions, there's no other side reactions, whatever. You're assuming all of the current went to turn A to B, but that's how you would do that calculation, basically. So
and also if you did do just like the first half of a cyclic voltammogram, your T2 would actually be at the end.
Oh, I didn't pick the right thing. Yeah, I should
it would just
put
be
further out or whatever.
Yeah, if you put it further out, because there's still still reducing or oxidizing, whatever it was, a plus electron gives you B.
Reduction. Yeah, I drew it up and it's an oxidation reduction, whatever.
Yeah.
So whether it's a negative peak or a positive peak, pardon the
Yeah.
convention here. Yeah.
Yeah. It's
For
just
sure.
all those other molecules at the end. Those are also undergoing a reaction. So that would be the total amount
Yeah.
of molecules.
He says that means he mostly did it right. That's good.
Okay.
Mostly
Yes.
right.
Yeah.
Okay, good.
Yeah.
Yeah. So
Good.
exactly where you pick the points would probably make the most sense. But I can tackle this next one
Yeah.
for you
Yeah.
too. So identifying features or regions of a Bode
Mm.
plot. So obviously it's going to depend on what data you're looking at. But that being
I
said,
do have Bode plots.
for a Bode plot, you are looking, generally speaking, I'll give you. I guess I'll make a Randles circuit and show you what a Randles circuit looks like, Bode plot wise, for typical values. Let me make it look not terrible for a second. That'll be there. Here, let's do that. Let's do this. There we go. So here's a Randles circuit. This is a kind of a typical Randles circuit. You might see there's a, on the right side, forget about the Bode. I'll talk about the Bode plot in a minute. I promise. I know that's what you asked. The semicircle plus a tail, that's a typical Warburg kind of a circuit. So on the Bode plot, mainly what you're looking for in the first case, let's just go away. On the phase angle, you're looking for the peaks, so to speak, on a phase angle go down if your phase angle plot is made properly, which is that it's negative phase angles going down. So the peaks going down, you see this one big peak, correlates to a semicircle. So another way to think about this is if you have two semicircles, two RCs, you should get two peaks on the Bode plot when I make these different values. So you see two peaks, two semicircles. So the peaks on the Bode plot will correlate with the semicircle. So that's the first on the phase angle plot. Now, the impedance magnitude almost all the time, unless you have an inductive weird thing, the impedance magnitude, so now you can go away, will always go up as the frequency goes down. It's typically logarithmic. Okay. When you have a portion of your impedance magnitude on your Bode plot where it's like this part right here, where it's like a straight line going up basically as the frequency goes down, that is a capacitor. That is the behavior of a capacitor. And you can see that it probably correlates with the peak, roughly speaking, right? The bottom of the peak of the phase angle correlates with this straight line. That's where it's most capacitive. That's basically the top of this semicircle, where the y-axis is the greatest. It's mostly capacitive. It's mostly out of phase. A pure capacitor looks just like this. It has just a straight line. That's like a pure capacitor. So a portion of your impedance magnitude that's a straight line correlates with just mostly capacitive behavior. Plateaus correlate with mostly resistive behavior. So there's a plateau at the beginning here, and there's a plateau at the end. That correlates to the start and the end of this semicircle. Okay. And that's the minimum of the phase angles. The phase angle is closest to zero. It's mostly resistive. And then the other part of this being the Warburg element does weird stuff. The phase angle will generally start decreasing towards 45 degrees as I go lower and lower. If I were to go lower in frequency, you'd see that. So there you go. Now it's minus 45 degrees. Voila. And the impedance magnitude also continues to go up at a slope, but it's a different slope. This slope right here is the one that correlates to mostly capacitive behavior. So you're looking for peaks, again, in the phase angle plot that correlate to the peaks, semicircles. You're looking for straight lines that correlate to mostly capacitive behavior over that frequency range. Plateaus that correlate to mostly resistive behavior over those frequency ranges. That's what I would say to you for Bode plot features.
Very cool. I rarely look at Bode plots, so it's nice to kind of like, oh yeah, that's right.
Plots are more fun.
Nyquist plots
you get loops and semicircles and inductive loops and inductive loops and inductive loops.
Are you trying to trigger me?
A little bit.
I was going to show you, like, when you just said loops, didn't even have to be inductive loops, just loops.
I had to say it multiple times. I can see the steam coming out of your ears. Alex hates inductive loops. Ask more questions about inductive loops.
No, I still don't.
They don't make any sense. But that's why they're funny.
That's why they're funny.
They don't make any sense at all.
And Mark Orsum's book is not like it's not like we're going to talk about inductive loops. Nope, they just talking about fundamental.
Talk about something else. Talk about things that make sense.
Oh, some of the stuff is still hard. Anyway, we have let's get to the next question. Hi, do we have a way to differentiate impedance from charge transfer and impedance from electrode-electrolyte interface from the EAS Nyquist plot? Thank you. Yeah, I mean, you actually kind of just had it.
Kind of just talked about
if
it.
you want to, I don't know if you just want to show the just the Nyquist plot again.
Yeah.
Like the semicircle has to do with charge transfer. Actually, so I guess you would say in the maybe the higher frequency region. I'm trying to think actually a better way. In Bard and Faulkner, they actually have they had a picture of it actually that kind of showed like this region of the Nyquist plot is for is more kinetics, and this region is more like mass transport diffusion. It's really like the tail is all mass transport diffusion, but
electrolyte interfacial. So I'm assuming you mean like the capacitance.
Yeah,
because you're asking how do you differentiate on the Nyquist plot between charge transfer and interfacial capacitance. Something like that.
Well,
that's how I see it. I don't know if that's exactly.
I know.
If that's what you're asking, that's what it seems like you're asking.
That might be what he's asking.
The charge transfer is the width of the semicircle, like Alex said. So the width of these semicircles, and in fact, you can see as I change this resistance value in the slider bar, the width of the semicircle gets bigger or smaller. So the charge transfer resistance on the Nyquist plot is just equivalent to the width of a semicircle that you observe. The interfacial capacitance is not easily observable on the Nyquist plot at all, actually. Watch as I change this value of the capacitance. Only at the extreme ends does it actually change. It's changing the spread of the points around the Nyquist plot, but it doesn't change the width or the shape of the Nyquist plot very much, actually. It can change the sharpness between when you have multiple peaks. If you only have one peak, it won't change very much at all. And only when you have like a really, really big capacitor, like it's like a semicircle that doesn't finish. The other direction is also straight. You don't see this very often, but it doesn't finish on the left. That doesn't happen much. But the interfacial capacitance is harder to view on the Nyquist plot. You view it more on the Bode plot. It's the position of the blue peak, basically, of the phase angle, like I just talked about. But very strictly speaking, the charge transfer resistance is very easy. It's the width of the semicircle. That one's pretty easy to identify.
Yeah,
thankfully.
All right. We have a question finally. We got to this one.
Yes.
From X. I know you're probably not there right now, but maybe you'll watch this later. Why don't we get complete semicircle plot and impedance done in aqueous potassium carbonate solution saturated with CO2? I think this is also another one of your potential triggering points, which is when one thing that might be happening is you are doing EIS at a potential where nothing is happening. So if you just have potassium carbonate at OCP saturated with CO2, if there are no redox reactions occurring, you probably won't get a semicircle. And in fact, if you look at just EIS of about or around the E naught of like a one electron reversible redox pair, like that's when you'll get a semicircle and like a Warburg diffusional tail. But then you can move, if you move away from the E naught, that semicircle will actually start to disappear. It'll get bigger, it'll get smaller, but it'll eventually start to disappear. Even if you go like way past it, so it's like, oh, you're definitely oxidizing or reducing something. It'll also won't show up because the charge transfer resistance is so freaking small at that point. You won't even see it. That was a problem I ran into a lot while trying to just like learn EIS. But that might be a reason. If you're not getting a complete semicircle, we would need to know what the frequency range is that you're working in. Sometimes you have to go from a very fast, like 1 megahertz, not even 100 megahertz, maybe 100 kilohertz. But you may have to go to the like hundreds of millihertz or tens of millihertz, if you're not going to that low of frequency, that may be another reason, again, depending on the RC time constant, if you will, of your system. That's my 2 cents.
Yeah, it's got to be one of those two things.
One of
It's
those
got to
two
it's
things.
it's or one of three things. It's that you haven't picked the right potential,
Mm-hmm.
as you said. That's the most likely situation, or you haven't gone to a low enough frequency,
Mm-hmm.
or it's that the charge transfer resistance is so large that
Oh,
it
it just
effectively can't. You
yeah.
won't see it finish. It would make a semicircle that would be so large. It's just hard. It's hard. It can't. It's beyond the impedance capability of the instrument, and that can be an outcropping of the first thing, which is that if you are trying to do CO2 reduction and you're not at a potential at which CO2 reduction is very favorable, it is the equivalent of saying the resistance to performing CO2 reduction is enormous, which is to say it's not happening because you haven't picked the right potential. So those are sort of the same thing, just stated a different way.
Yes.
Thank you for answering that.
Yeah.
I would have started foaming at the mouth.
Yeah, I know. Because it's like, well, the answer, I think I know what the answer might be, and it's
glad
what you
that
don't like.
Yes, it's the thing I hate.
Let's see, got a couple comments. This is good.
Sam.
Yeah, Sam has a question. Could you talk about how changes in the electrical double layer thickness would affect peak quantity, relaxation time, and impedance magnitude?
Changes in thickness.
Peak quantity. Peak
I
quantity.
think it would change the peak quantity. The electrical double layer is the background current of a cyclic voltammogram. So if you're talking about CV peaks, it wouldn't change peak quantity.
If it's anything, the electrical double layer thickness is almost like having I want to say a really small capacitance.
Yeah, because if it's like a really thick, it's like a big distance.
Yeah.
And capacitance is inversely related to the distance.
Yeah.
So if it's a thick layer, it's a low capacitance.
Yeah.
So,
if it's
but again, peak again. I don't know. Do you mean CV peak or you mean a peak in a Nyquist plot or Bode plot or something?
Yeah.
Relaxation time.
If it's a lower one, it'll relax faster.
Yeah, if it's a smaller capacitance, thicker layer, in theory, would lead to a smaller capacitance, which means the RC time constant is smaller, which means that it relaxes faster.
That's our interpretation.
That's my interpretation. And then the impedance magnitude would be higher. A smaller capacitor would lead to larger impedance for the same frequency, all things being equal. So that, I think, is the answer.
Yeah, that's right. Small.
That is our best reasoning throughout all of those things.
Yeah,
would be my guess.
That's our thought.
Yes. Oh, in DRT. That's a good question. I have had this. I tried talking about this the other day. I should pull up. You should answer a question. I can pull up a paper. The DRT peak. I had mentioned this. So like there is a quantification that you can do with DRT peaks, and I can't remember. I read about it recently, and I think I saved a paper on it, and I'm going to try to find it. Maybe while Alex answers another question and lets me stall here.
I can. Although I may have to skip Anonymous Wombat because I don't know enough about DRT to really comment on it. Actually, most of the questions are kind of EIS. There's a question. Oh, maybe I can talk a little bit about this.
Okay, so sorry, I found the statement that I was looking for. So this is, I'll share this. This is from this is from a paper. So just giving credit where it's due, I'll give you the reference in a moment. But this is the statement that I found. So the area under each specific peak corresponds to the impedance contribution of the underlying process. So when you have, this is what the thing I couldn't think of the right wording like last week or the week before when I was talking about this to describe this. But effectively, when you have a DRT, a set of peaks, is there a plot in here with them? It's all mathematics in this paper.
Fun.
I was trying to see if so like here, this green one here. So the impedance of each process is correlative to the area under each of the peaks. So based on the thought train we just went along, for example, a thicker electrical double layer would in theory lead to a smaller capacitance, which leads to a larger impedance, which means the peak in DRT would be higher.
Like the area under the peak would be higher.
The area, which means the peak would probably be higher itself because the area is higher. Like, you know what I mean? It could be, it could be broader or taller.
Yeah,
but my guess is that because the impedance is greater and the area under the peak, as I said, which is in this paper, they describe that the area under the peak is proportionate. Where the heck was it? I go past it. I can't remember. I think I went past it. The area under the peak. I have no idea where it is. Cool. Where the heck was I? I don't know where I was. Sorry.
Quant.
I know. I was like looking for quantification. The area under the peak. I had it. Where did I? What? How did I lose my spot? I lost my spot.
This is when you're talking about what the.
Yeah, no, it's just a spot in the paper with the phrase. I just like the way that they word. It's very succinct. Where they wait, here it is. Here it is. The area under each specific peak corresponds to the impedance contribution of the underlying process. So just again, in short, the impedance of that process, in other words, greater impedance means it's like not as good, which means a smaller capacitor has higher impedance. It should have a bigger peak in the DRT. So that's my guess, I guess you'd say, based on knowledge of DRT.
Okay.
And I'm going to put the DOI for this paper so I can give credit. This is a paper called Optimized Process Parameters for a Reproducible Distribution of Relaxation Times Analysis of Electrochemical Systems by Marcus Hans, Stefan Schindler, Lisa Charlotte Trebes, and Michael Donzer. They're a group from Germany.
All right.
Here is the reference. I'm going to put it in there. Give proper attribution. Okay. This is the paper on DRT paper. There you go.
Well, here, the next one, we got Anonymous Wombat again.
Excellent.
And we will get to Ranjana's question soon. But Anonymous Wombat asks, thank you. I work with solid-state batteries. I suspect I see a peak from charge transfer from my metal anode electrolyte interface. Do you have any suggestions to verify that the DRT peak is from charge transfer? CT.
So that's somewhat definitional. If you see a peak with DRT, it means there is a charge transfer process. So if you have multiple peaks, which one correlates to which might be a question that I don't know if I can answer perfectly, but if you see a peak, I think it sort of definitionally means you have a charge transfer process. It sort of definitionally means you have an RC, which is a charge transfer process with some coupled capacitance. It's kind of definitionally true, assuming you're doing DRT correctly, which is to say that you don't have any inductive processes, you don't have any pure capacitive processes, and you're not applying DRT through diffusional or Warburg processes. You only want to analyze DRT data through charge transfer processes, basically, semicircles on an Nyquist plot. That I think is the answer. I think it definitionally means that you do have a charge transfer process, but I guess I don't know 100% for sure. I'd have to probably know more about your system or know more about the specific thing, I guess, going on. But that's my understanding of it there. So I believe it does mean you have that it's charge transfer process. I believe.
All right. Ranjana, all right, we're back. What does it mean when the left side of the semicircle does not touch the x-axis in a Nyquist plot? And what potential should the EIS experiment be conducted? She is referring to EIS, a hydrogen evolution reaction in a KOH solution. Well, I would guess generally speaking, I'm just kind of thinking about when you have an Nyquist plot and you have your
if the semicircle doesn't touch the x-axis on the left-hand part of it, it means either your capacitance is too small or there's an instrument artifact.
Yeah, so it's not at the zero.
Well, so that's one possibility, right? If it's like
yeah.
if it's like a semicircle, that would complete in negative territory. Like you could draw a
Oh,
little tail, like it
I
goes
was just thinking
down
about
and then
this one.
up.
Yeah, something like
Exactly.
this.
Yeah.
That's what. Yeah, and you're only measuring this.
Yeah, or anywhere from the positive. If it's like
Yeah.
that, and if it would complete in the negative territory,
Mm-hmm. Then
then
it's an
it's
artifact.
an artifact.
Oh yeah, we saw this on the last live stream. Somebody showed us a paper from an email, and we thought that like, oh, because they thought they were doing things wrong,
Right.
and we think that they were doing things right because all the EIS data was starting here.
Right.
So,
Right. Right.
so we thought that may have been an instrument artifact
Yeah.
or something else.
Strictly
But
speaking,
yeah,
though, if it doesn't, and it would finish in the real territory, but it just doesn't fully complete itself from the left, basically.
so it's like this, and it didn't.
It didn't quite touch. Yeah, it might
and
be
it
more
didn't quite
dramatic
touch.
than that. Yeah, exactly. But
Yeah.
essentially, if it doesn't touch, it means the capacitance is very, very small. That's what it means.
Yeah.
So it means you have a charge transfer process with a very, very small capacitance. And to probe very small capacitances, you have to use really high frequencies because otherwise the impedance of it is so great that the capacitor is bypassed and virtually unmeasurable. So sometimes that happens. It's pretty rare, but it's possible to have a very, very fast process with a very small capacitance and a very, very short time constant.
Yeah.
And so you need like really high frequencies. Sometimes that can happen with solid state systems because the frequencies can be very, very you need fast frequencies to probe them because the time constants are so small.
But because she's working in KOH,
probably not the case.
It's mostly the former.
It's most likely an
It's
artifact.
most
That's
likely
correct.
the former.
Most probably. And what potential should you do it at? What are you trying to study? Hydrogen evolution?
Yeah, hydrogen evolution.
Pick a potential where that's happening.
Yeah.
So it happens at 0 versus NHE. If you're in KOH, the pH goes up, so the potential at which it occurs goes down. So if you're at like pH of like 14, then versus NHE, the hydrogen evolution reactions occurring at about -3 to 400 millivolts, and then adjust for whatever reference electrode you have. Pick a potential around there if you want to study hydrogen evolution. Otherwise, if you pick OCP, you're not really studying anything.
Yeah, Ranja has a comment. She said, "Thanks so much. The second situation is happening to me, and she's already using 1 megahertz. Can I go higher?"
So my follow-up question is, well, first of all, if your
Oh.
potentiostat can go higher, most potentiostats can't go too much higher than a megahertz. And secondly, why does it matter? Why do you need to finish the semicircle? Is there a reason? It doesn't have, you don't have to start at the x-axis. You can probably do a circuit fit, for instance, and get a fit for that first semicircle, for instance, if it is something that has just a very, very small capacitance. And you can still model your data unless there's like not nearly enough of the semicircle to fit. But if you have some of it, you can just do a fit on it. Because even if you can go above a megahertz, it's very likely the data will be very, very inaccurate. And you might not get very good quality data above a megahertz. So it's probably not necessary, to be honest with you. It's probably not even really needed. I don't know that you need to worry so much about that.
I would also say one thing I've observed when I first started doing some EIS was like the potentiostat may default to a quote non-orthogonal view. So it's just going to try to put the data point on a place where like everything looks very nice and even and you can see stuff. It may be the case that like, oh, everything to the right is like kilohertz or something, or not kilohertz, kilo ohms of like resistance. But really your imaginary impedance, it's not being on the x-axis, is like 1 ohm of imaginary impedance. It's effectively like in the noise, sort of say, but it doesn't just look like it's crossing the x-axis or at the x-axis. That's another thing I would double check the axes and plot it orthogonally, just to make sure. Yes. So let us know if you have any more questions. And we got a comment from Barry. Barry,
hey, congratulations!
Good to see you, Chum. I'd like to thank you. We recently got a paper published, and my undergrad did all the work. That's fantastic.
That's amazing. Undergrads doing work for publications is quite impressive.
Actually,
It's unusual.
do you want to send us the DOI in the chat and we can promote it? Well, I mean, we'll just promote it right here, just whoever's watching
if it's
it.
not
If it's not
totally
if it's
published
okay.
yet, or you can't, that's
Yeah,
fine.
that's
But yeah,
also
we'd be
true.
interested to see what it is. But,
Yeah.
I
But
mean,
he said published, not
yeah.
accepted.
No, I
So
know
I'm
that's true.
assuming,
But like sometimes it's in the publication process and the DOI isn't done yet. You know what I
Yeah,
mean? Like it could
that's
take
true.
some time for that to be or whatever. But
That's
yeah, if
very
you have
true.
the DOI, send it along.
Yeah. Oh,
Be happy
congratulations.
to take a look. Congrats.
That's very good. Wow, we got a lot of people ask us a lot of questions in just kind of rapid succession.
Yeah, I think we got to them though.
I think we got to
Hopefully
all
we
of
got to
them. This is good. And I'm glad everybody asked their question when they did, because next week is the US holiday, Thanksgiving, and we'll be closed that day. And so we will not be doing the live stream during that time. And the following week is the MRS meeting. So the week of December
something.
2nd to December 5th.
Yeah,
or
I think I
something.
should be back though.
Oh yeah, I'm just saying you should
that's
see
right, yeah.
Neil at the MRS meeting if you're going to the Material Research
It's in
Society conference
Boston,
in Boston.
Massachusetts. So
Yeah.
yes, I will be there with my colleague Tim.
Yes.
And I will be in the exhibition. So come say hi if you're there. The Materials Research Society meeting, and then I think I should be back Thursday. I think I'm coming back at some point, so I should be in Friday. So we should. So in other words, the next live stream here will be in 2 weeks.
Yes, yeah. If you're hoping to ask us more questions, and if we don't get to your questions now, just leave them in the comment section. We will get to them.
Yeah.
For the next live stream.
Did you want to get to some of? There's a couple from.
That's actually a good point.
We have like maybe 10-15 minutes.
Yeah,
to get to.
We do have that.
We had a couple, I think, from last week again.
Aziz,
Izaz.
I mispronounced that.
I think anyway.
Yeah. Oh,
again,
okay.
We mispronounce things.
That's what we mispronounce names. Sorry.
Yeah. So he said, "Is the gel connection?" Was the bottom one the first one? Actually, I think the bottom one.
Yeah, let's go with the bottom one first.
Order. Yeah. Hello, sir. I am working on hydrogels as an electrolyte in batteries using AutoLab with a 3-electrode setup. We use hydrogels as a working electrode to perform the CV and GCD measurements. So the question was, I guess, is the gel connection to the working electrode the correct way? And I do not understand the proper window for CV measurements. If the gel connection is not correct, then how do we do that? So that doesn't sound right, only because if you're talking about you're using the hydrogel as an electrolyte, then no, you're not connecting the electrolyte to the working electrode. The working electrode is the cathode of a battery. So if you're working in a 3-electrode setup and you are testing some battery electrodes with hydrogel electrolyte, the electrolyte's the thing in between the anode and the cathode. I haven't worked with hydrogels personally. I know it's kind of like it's not solid, but it's a gel matrix of some kind, right? So you can connect one way or another. But the point here is that I would say, no, you should be connecting your working electrode of your potentiostat to the cathode, the counter electrode to the anode, and the reference to the reference electrode, and then do your experiments that way. When you have a negative current in that situation, you are discharging the battery, and when you have a positive current, you are charging. So that's like the set of connections and magnitude of or whatever positive, negative of potential and current that you would expect to see. If you want to talk about the potential window, you've talked about that before.
Oh yeah, I can do that.
As far as what the potential window you should be using for CV, a lot of times you can determine that experimentally. So with a battery, it's a little different because the scans that you're going to do are going to be very slow. And a lot of times you want to couple that with knowledge of what the charge discharge redox processes are beforehand, if you can. But I mean, I don't know, we can draw it or we can just sort of talk it through. But I mean, basically you're going to just scan a little bit positive, a little bit negative, and then you're going to sort of increase that window a little bit on either end. Alex can draw that as
I'll just draw it as you describe it. If you're doing CV and you have a voltage, current, you might start very small, and let's just say this is 0 for now. I don't know for sure for your system, but you might want to scan like here, and maybe this is like 200 millivolts. Or sorry, this is like minus 200, and this will be plus 200. And then you want to go like a little bit further, and then you're going to get these kind of like boxes. But then eventually, as you keep scanning, you're going to kind of start to see these like tails show up. And now I'm doing kind of like the IU-PAC method. And it's like once you start to see this, generally speaking, you now want to be a little bit more cautious, because what can happen, and this may not necessarily be symmetric, right? It's not going to be the case that, oh, when I'm at 600, right? When I'm at 600, oh God, 600, this is going to be also minus 600. It may be 300 or minus 300, and this is 800. It could be bipolar in that case. It all is based on, your reference potential and things like that, and what reactions are occurring in this particular case. So once you start to see this, and then you can do an experiment where you're like, oh my God, it gets really, really high, and then this is like, oh God, it gets really, really low, and then oh, this is where I need to stop. This is my potential window, because I'm getting like milliamps for a little 3 millimeter disc electrode. That's a lot of current. If you're getting nano or microamps, it's okay. It kind of depends on the size and stuff, but that's how you should experimentally determine it. Just slowly increase your potential range until you start to see a lot of current buildup, and that may be your electrolyte breaking down, your working electrode breaking down, those kinds of things. So it's best to determine the potential window in CV empirically by actually just doing CV segments back and forth.
Yeah, and especially because it'll change for a lot of things. What the reference electrode is, what the pH is. You're doing a hydrogel, so your battery electrode's a little bit. Electrolyte is a bit unknown, I guess, in some ways. And then whatever the reference is, it could be unknown where your potential window is, going to lie. So it's good to check that empirically, like Alex said.
We do have a question in the chat from Mustafa from LinkedIn. Thanks for stopping by. Mustafa asks, what distinguishes Faradaic reactions in batteries from pseudocapacitance in supercapacitors? In both processes, electron transfer occurs, but how do they differ? I think this is a very good question. It's something that we are currently learning more about. I have tried to read some papers about it, and recently I came across, I actually met this professor, Veronica Augustine, and she was a graduate student of the person who founded the Dunn method, Bruce Dunn, and knows way more about pseudocapacitance. I don't know. I want to at least let me at least just I guess I can just share the DOI of this publication.
I think the short answer while you find the DOI is that, it's a difference between a Faradaic and a non-Faradaic charge transfer, which is to say that aside from the phenomenon of pseudocapacitance, if we just think about capacitance more broadly as a non-Faradaic process, it's the buildup of charge between two oppositely charged plates or planes with a dielectric material in between. And the Faradaic process, and you've talked about this with more detail than I'm aware of, the difference between what a heterogeneous and homogeneous electron transfer, whether it tunnels through or which is a heterogeneous process, or
it's heterogeneous when you have like a bond, like almost like a chemical bond,
right,
to the surface, and it's electrode, it's potential and electrode dependent.
Right. Otherwise, it's a homogeneous process if it tunnels through
if it kind of tunnels through the
got
solvent.
it, right. I for some reason always
no.
But the point being that the Faradaic reaction is that kind of process where there's a direct electron transfer between whatever reagent and electrode surface or
Mhm.
something like that. Whereas the charge transfer or the charge buildup, if you will, with a capacitor is through a capacitive process, which is a buildup of that's it's sort of definitional, right? It's just,
Yeah,
but I don't know if you want to talk more about it.
well, this is just, and I'm still learning about this. I want to show this chemical reviews paper. I have not read it yet, but it was because it was only given to me like maybe a little more than a week ago, and I just had a lot of other things going on. But I'm hoping that I put the DUI in the comment section, so hopefully you received it. And this is, I think this paper, this review article, will actually shed more light on not only what pseudocapacitance is, but also a little bit of its history. Like, where did this phrase come from? Um, but what I've learned, I guess, very briefly about pseudocapacitance, my thought about this is I think they're actually very similar, sort of say. Um, but of course, as Neil said, capacitance is when you have charge separation, um, and you're storing charge where there's no electron transfer between them. Pseudocapacitance is a combination of stored charge transfer, or sorry, of stored charge between like two plates, but also a Faradaic reaction can occur, kind of resulting in more capacity, I think, than if you just had like the electrical double layer. And pseudocapacitance, and so there's like three forms. I think they're similar in terms of the kind of electron transfer that happens in a battery versus a supercapacitor, versus just the traditional electrochemistry that we learn. One's this intercalation process, like, oh, like intercalation, the ion moves into the phase of the species, like lithium ion intercalating into carbon.
Yeah.
Like, you could have lithium just at the carbon interface, just waiting there, and then it intercalates, and then you start to get the charge transfer to occur. So you could build up charge until the intercalation occurs, and that's a redox process. Um, the professor was telling me that atom adsorption, so like under potential or just potential deposition, like single layers of atoms undergoing an electron transfer at the surface, was also a form because you could oxidize it and you could get the electrons right off, and it was just only at the electrode surface. So um so I think there actually is a little bit of a blend, Mustafa, between the Faradaic reactions at batteries and the Faradaic reactions of supercapacitors and pseudocapacitance. One thing that I just learned from Neil was that as you're charging or discharging a battery, the intercalation is going like deep into the material.
Mhm.
Like the lithium's going like all the way into the material.
In fact, it works kind of something like this.
Yeah.
I'll sort of draw. I can't really like animate it properly,
Yeah, yeah,
on
yeah.
the fly, but you can
Mhm.
imagine, for instance, as you intercalate lithium through graphite, if these are where the Li pluses are, and they're moving into the graphite, and then at the very base, this is my current collector. So this is the solid, whatever, right? This right here is the graphite layer, and so it's this thick. It's like after a short time, it's like this much is intercalated. Then after a little bit while longer, like this much is intercalated, and then after a little while longer, this much is intercalated, and you get gradations because it's kind of like this will be like you have like LIXC6, so it's almost like you can imagine like the part that's closest to where all the electrolyte is like Li1, and then this part in here might be like Li.8 at any like snapshot in time, and this might be Li.6. It's like there's some time lag or whatever associated. It's like almost like a
Yeah.
gradient of intercalation or whatever. And so a lot of times what we're talking about is we have like 50% state of charge. It's like part of the lithium might be fully intercalated,
Yeah.
part of it might be almost not at all. And it's just because it doesn't all, there's no guarantee that 100% of the lattice, like if I have Li 0.5 C6, that's like 50% state of charge. That doesn't mean all parts of the lattice of my carbon are like 50% intercalated, right? All of it. It's like you might have all this is 100%, and then this is 0, and then in the middle is 50, and then this is like 75%, this is 30, 20%. You know, it's like there might be a distribution, for instance.
Okay. Yeah.
That's kind of what we observe when we do this. Anyway, so
Yeah.
the as a result of that, you probably do have a lot of situations where locally you have some pseudo-capacitive effects where you have almost charge buildup because it's not all equally distributed.
Yeah.
If the layer is really thin, it probably will be, but usually it's somewhat thick, and then you get sort of that process occurring. Yeah.
Yeah. So Mustafa, I hope this is helpful. Continue to ask us questions on LinkedIn. We appreciate it, and force me to read and learn more about pseudocapacitance and things like that. But I hope that article is a review is helpful. I think we just take this one last question from
I think that's
DF.
It. Yeah, last one here.
I have another basic one. I want to do cyclic voltammetry or even FSCV, fast scan cyclic voltammetry, but I can only use 2 platinum electrodes, combining a reference and counter. Is this fundamentally wrong? I can make my reference and counter way larger than my working. You can do this. We don't know exactly what kind of experiments you're trying to do. I know it's just CV, but you can use 2 of the same type of material working electrode, and then apply a voltage difference between them. You will not know exactly what the potential is necessarily of one of your working electrode that's platinum. With respect to platinum, you'll only know the voltage difference between them, which is fine. And as long as the reactions occurring on that reference counter electrode don't interfere with what's happening on the working, then you should be okay. We typically make the area of the counter electrode much larger than the working area, because we want to, there must be charge balance for any oxidation or reduction reaction happening on a working electrode. There must be an oxidation or reduction reaction, a counter reaction occurring on the counter electrode. So the large area is just to make sure that process can occur. Otherwise, you'll run into a compliance voltage issue. But if your potentiostat has a sufficiently high compliance voltage, you don't always have to have the biggest reference and counter electrode compared to your working. But it's recommended. But yeah, hey, give it a shot. See what happens. I don't think there's anything fundamentally wrong. Like you'll get some data, definitely.
Yeah, it might shift around because the reference is sort of who knows. But yeah, you can get perfectly good data. Well, you can get data.
You can get data.
I don't know if it's perfectly good, but it's data.
It'll probably you'll learn something.
That's true. You will learn something, and at the end of the day, we're all here to learn. See how I wrapped it up?
Yeah, that was a great wrap up.
It was so corny. It was so bad. I'm very sorry for that. I'm not sorry at all. I hope everybody enjoyed this episode. Thank you all. I hope we got to everybody's question. Even if you had to wait a little while, I do apologize. We had a pretty good onslaught of questions, and so very much appreciative. And I just always feel bad making people wait. But as you probably know, if you're asking questions about electrochemistry, it's not always something you can answer in 2 seconds. It takes a little time to explain processes and whatever. And so we try to do justice to the questions and answer them as thoroughly as we can, obviously. So that being said, like we said, thank you, everybody. With no live stream next week, I hope if you are in the US or not in the US, you should enjoy Thanksgiving anyway and have a turkey or something, have some pie, whatever. And I will see anybody in Boston if you happen to be there. Otherwise, we'll see you in 2 weeks at our next event here, and everybody should, I guess, take care.
Yeah.
Bye.
Bye.